I'm Gary Pocock, and this is my Week 11 reflection for the Physics Modelling course. This week I'm continuing my reflection from last week on how energy is transmitted through an electrical circuit. Last week I surveyed the standard textbook explanations and found that there were problems with them. My conclusion was that the standard textbooks accounts are vague and inconsistent, and most importantly there appears to be no mathematical model that supports the explanations that they are giving. So this week I want to look at the explanation that is supported by a mathematical model, and this is the Poynting vector model. And when I first came across this, I was absolutely amazed. This is a very, very surprising explanation. Okay, so what is the Poynting vector? Well, there's the mathematical definition. It's the E cross B field, and typically this is introduced to physics students via the context of electromagnetic waves. We have the E field and the B field oscillating at right angles to each other, and energy is transmitted in a direction that is perpendicular to both the E and B fields, so in other words in the direction of propagation. It turns out that you can apply the same concept to explain energy being transmitted through an electrical circuit. As far as I can tell, this is the earliest proposal for this. No, sorry, not the earliest, but the second earliest was Feynman in his lectures. And here he says, what happens in a piece of resistance wire when it's carrying a current? Okay, there is an electrical field inside the wire, and then he also adds there is an electrical field just outside the wire parallel to the surface because there is a potential drop across the wire. I don't understand that explanation, but I would say there's an electrical field just outside the wire just because of surface charge. Now apparently the surface charge model wasn't really very well known then, and Feynman wasn't aware of it, so he doesn't mention it. Alright, so we've got an electric field just outside the wire. We've got a B field created by the current, and that produces a Poynting vector pointing into the wire. So in other words, energy is flowing into the wire from outside the wire. Now you notice that Feynman calls this in scare quotes his crazy theory. So he seems ambivalent about it. He keeps saying it's true, but I know it's crazy. Intuition would seem to tell us that electrons get their energy from being pushed along the wire. But theory says that the electrons are being pushed by an electric field, and that the electrons get their energy from this same field. The energy somehow flows from distant charges into a wide area of space and then inward to the wire. And I read that, I was absolutely amazed. He wasn't the first to propose it. The first person to propose it was Sommerfeld, and it's published in his 1952 lectures. Presumably he died in 1952, so presumably he'd worked that out quite a bit beforehand. But he'd only worked it out for the ideal case of an infinite length of straight wire. As far as I can tell, it was only in the 60s that a fully worked out count was developed. So I've found a paper on it and published in the American Journal of Physics. And so what I'm going to try and do is work my way through this explanation. Okay, so here are their diagrams. Oops, let me expand this diagram, and I'll just get this page display to scroll. Okay. Alright, so how does this Poynting vector model explain energy transmission in a simple electrical circuit. Okay, so these authors, Galilei and Goibag, start off with a battery connected to a wire. They've drawn in the surface charge, and then they've drawn the electric field inside the wire, which they're calling the tangential field. And we know, because the current is a constant value, that this tangential field must also be constant, hence the arrows are all the same length. But in addition to this tangential field, and the tangential field is all that traditional accounts consider, but now we say let's look at the normal component of the electrical field, and it must have a normal component because a wire, after all, is just a cylinder, so there would be an electric field radiating out perpendicularly from the wire. But this one is, the perpendicular field is not constant. It varies according to the concentration of surface charge. So when we have a high concentration of surface charge, the perpendicular component is large. When we have a low concentration of surface charge, the perpendicular component is small. So the net electric field changes direction as you go around the wire. Alright, that's the first step. Now we move on and we look at a circuit containing a resistive element. And to simplify things, they've assumed in this diagram that the wire has zero resistance. So the tangential component of the electrical field in the wire has disappeared. Zero resistance means the electrons no longer need a field to propel them around the wire. The normal component of the electrical field in the wire remains. Again, varying in size according to the concentration of surface charge. When we hit the resistive element, the tangential component obviously returns. You need a field in the resistor to push the electrons through the resistor. So now your net field inside the resistor, which is these grey arrows here, changes direction as you go through the resistor. Downwards angle here, horizontal in the middle, and pointing upwards on the right hand side. Meanwhile, the normal electrical field radiates out on this side of the resistor, and when electrical surface charges dominate, negative surface charge dominates, the normal field points into the wire. Okay, so that's the full story of the electric field surrounding a wire and resistive element in the circuit. Now let's move on and introduce the magnetic field. Okay, so in this diagram, just for clarity, they've drawn the E and B fields on the outside of the wire only. There are obviously E and B fields on the inside of the wire as well. So here is our net E field taken from the previous diagram, radiating out from the wire and radiating in on this side, and changing its angle as it goes through the resistive element. The B field is caused by the current flowing through the wire, so we use our right hand wrap rule and we get B fields on the outside of the wire that are going into the page. We now use our other right hand rule to work out the pointing vector. Pointing vector is E cross B, and when we apply our right hand rule we get pointing vectors as indicated by these grey arrows here. Okay, several points. First of all, the pointing vector is also running along the outside of the wire. That's just not being drawn for clarity purposes. Second point, the pointing vector curls into the resistive element because of the changing direction of the E field as you go through the resistor. So you get a quite remarkable result. The energy is flowing out of the battery in both directions, outside the wire, and then into the resistor or light bulb. It can flow also straight across. However, as you can see on the sentence I've highlighted over here, the strength of the pointing vector decreases as 1 over r squared. So that means most of the energy is running along the wire very, very close to the wire and then going in to the resistive element. That's, I still can't believe it. I can understand why Feynman was putting scare quotes and calling it a crazy theory. Energy is flowing outside the wire. There are various ways of making this plausible. The standard way of doing it is reminding students about AC current and transformers and how energy flows through space in a step up or step down transformer. So we are all familiar with the idea that electrical energy can flow through space. So it's actually nice that you have a flowing through space account that works for DC circuits as well as for AC circuits. Now the other paper that I mentioned, the Sefton paper, he comments on this, and he comments on Charbet and Sherwood's surface charge account, which he thinks is great, and then he says, surprisingly, Charbet and Sherwood do not go on to give this pointing vector energy explanation, and he thinks they should have done that. And I would suggest that in the next version of the modelling instruction notes for E&M, that this explanation for energy should be included in the modelling notes. How exactly you could develop an experiment to demonstrate it, I am not sure. But it's such an amazing account, and not too difficult. It's simply an E cross B vector, but you must take into account the field outside of the battery, and that's something that is largely ignored in the current modelling notes. So there you have it. What prompted this exploration of mine in the first place was my struggles with the Unit 3 notes, modelling notes, and I just felt I wasn't getting the clarity that I needed, and I decided that one area that was lacking in clarity was the energy story. And so I went out and tried to write my own energy story, and I found I couldn't do it. And that set me searching, and that's how I came across this story about the pointing vector.